Hello everyone, this is part 2 of section 14.9 Lagrange multipliers. Last time we saw the Calc 1 example of a word problem, and we saw the special theorems and procedures here for solving these multivariable word problems or constraint problems, and we did see this one example. So we'll continue with more examples, and basically, as you can see, we just took the constraint, set it to 0, we're given the function, formed the special function that we call uppercase F, and took each partial, set them to 0, solved the resulting equation system, and then we just determined if we had max or mins based on the functional values. So pretty much the same thing with this next example. Here we'll have g of xy, I'll set it to 0, so x plus y plus z minus 1. Here's our function f of xy, and actually it's f of xy and z. So that's a little typo there. See if we could squeeze a z in there. Okay, so it's a function 3 variables. So now we're going to form f of x, y, z, and lambda. So that's going to be f of x, y, z, and then minus lambda times g of x, y, z. So I suppose this as well should be g of x, y, and z equaling the x plus y plus z minus 1. So then our function becomes f of x, y, z was x squared plus y squared plus z squared, and then minus lambda times the g of x, y, z was x plus y plus z minus 1. Okay, so now we need our 4 partials. So f sub x, 2x minus, because the y squared, z squared are constants, derivative of x is 1, these are all zeros, so just 2x minus lambda, f sub y, 2y, because x and z are constants, and then derivative of y is 1, so 2y minus lambda, and similarly f sub z, looks like it's 2z minus lambda. And then f sub lambda, the partial with respect to lambda, remember it's always really just minus whatever g of x, y, in this case x, y, z was, but that's just because lambda's derivative is 1, and that negative gets distributed. So minus x minus y minus z plus 1. Okay, and then it's usually, then we need to set these to 0. So 2x minus lambda is 0, 2y minus lambda is 0, 2z minus lambda is 0, and minus x minus y minus z plus 1 is 0. And then to solve, maybe consider these first 2 equations solving for lambda. We get lambda is 2x and lambda is 2y. So setting the lambdas equal, 2x equals 2y. So then x is y. Here we have lambda is 2z, then let's say that we took the 2y, setting these two equal to each other, we could say 2y equals 2z, so y is z. So that basically tells us, these two equations that we found basically tells us that x is the same as y, which is the same as z. So then if we take that and we substitute, it doesn't matter how you substitute, x, y, and z are all the same. So maybe you would just say minus x minus x minus x plus 1 is 0. So minus 3x plus 1 is 0. 3x would be 1. And x is 1/3. So then x is the same as y, so y is 1/3. Let me do it that way. So y is 1/3 and z is 1/3. And then to basically determine that it is a minimum, and a lot of times really whatever they're looking for, mins or max, that's what you're finding. And you pretty much stop right there and I'd be satisfied. But we'll check the functional value. F of 1/3, 1/3, and 1/3 gives 1/3 squared plus 1/3 squared plus 1/3 squared, because x squared plus y squared plus z squared is the function. So that's 1/9 plus 1/9 plus 1/9, which is 3/9, which reduces to 1/3. And you could determine that it is, in fact, a minimum. Let's say as a little check here. Maybe just pick a point that satisfies this equation. Like, for example, when x is 1, that satisfies both of these equations, that is. For example, when x is 1, y is 0 and z is 0, the function would be 1, and the constraint would be true, that x is 1 when y is 0 and z is 0. So then it does verify that f of 1/0/0 is 1, which is less than 1/3. So then it's a relative minimum. But once again, you really don't have to worry about this portion. Just solve the system and, solve the system, and whatever you come up with will be what they're looking for, either a max or a min. Okay, so a couple more examples. Okay, so here's an example of finally a word problem. So we have a cylindrical can is to contain a volume of 1,000 pi cubic meters. So if you want to draw this little can here, the volume is 1,000 pi cubic centimeters. I'm sorry, not meters. That'd be a pretty big can. So we want the dimensions that will minimize the surface area. So therefore, our objective, or the primary equation, so primary is often referred to as the objective equation. Okay, we want to minimize the surface area. So the surface area for I would give you these formulas. You're actually going to have an example on the exam that's similar to number 2 or maybe number 4, as we'll see. But something where you're given the function and the constraint equation literally, and you don't have to build it. But some of the problems in the homework are a little more challenging, like this one. So the surface area for a cylinder. You've got the top and the bottom, and they both have an area of pi r squared. But let's say that the top is open. So we just have 1 pi r squared. And then we have the around the outside. And around the outside, well, the circumference is 2 pi r for a circle, so this is our radius r. The circumference is 2 pi r, but then we're translating that through a height of h units. So we'll say plus 2 pi r h. Okay, so that's the primary and the objective equation. The secondary, or the constraint equation, is the fact that the volume is 1000 pi. But the volume of a cylinder is pi r squared h. So pi r squared h is 1000 pi. So therefore, we basically have g of xy here, or g of RH, I should say. We'll take it to be pi r squared h minus 1000 pi. And we'll call the surface area the F of RH. So that our function now would be, in terms of the variables, r, h, and lambda. So uppercase F of r, h, and lambda is going to be the pi r squared plus 2 pi r h, and then minus the quantity pi squared minus 1000 pi. Okay, so now we need the partials. So 3 of them here. First partial with respect to r. This would be 2 pi r. Because the derivative of r squared is 2r, so 2 pi r. Here the derivative of r is 1, h is being held as a constant, so plus 2 pi h. And then here we have derivative of r squared is 2r, so minus 2 pi r h. So that's for the partial with respect to r. If we take the partial with respect to h, okay, this term goes to 0. Here we get 2 pi r because the derivative of h is 1, and then minus pi r squared. Oh, I forgot to mention derivative of 1000 pi, that's just a constant, so that's 0. Okay, then finally, the partial with respect to lambda is just going to be minus this quantity. Oh, I forgot to stick my lambda in there. Make sure you fit the lambda in there. Because formally, like I say, I also forgot to write this. F of r h lambda is going to be f of r h minus lambda times g of RH. Okay, so that was where we got that from. And then minus, so minus square root of lambda is 1. So distribute the negative pi r squared h plus 1,000 pi. Okay, so looks like I lost my lambdas here then. So therefore, we would have to have a lambda associated with the 2 pi rh. Slide that lambda in there, and then also with the minus pi r squared. Okay, so please make note of what I'm pointing out here. The fact that I forgot my lambda originally caused all of those things to change, right? Okay, so let's solve each of these for lambda. So we'd have, well, first we'll set them to 0. So 2 pi r plus 2 pi h minus 2 pi rh lambda is 0. So we'll have 2 pi r plus 2 pi h equaling 2 pi rh lambda. So 2 pi r plus 2 pi h over 2 pi rh is lambda. And if we factor 2 pi out of the top, we're left with r plus h, and then over the 2 pi rh. Now we can cancel the 2 is lambda. Now we can cancel the 2 pi's. We get r plus h over rh is lambda. Okay, so then if we set f sub h to 0, 2 pi r minus pi r squared lambda is 0. Solve for lambda here. So 2 pi r over pi r squared is lambda. We cancel the pi's and one of the r's, and we get 2 over r is lambda. So then if we set these two equal to each other, lambda is equal to lambda, r plus h over rh is 2 over r. And then from there we'll cross multiply, so r squared plus rh is 2rh. And see, subtracting rh from both sides, we could have r squared equaling rh, and dividing out an r would be equal to h. So now we'll use f sub lambda. Okay, so that's a lambda. That was way back up here, negative pi r squared h plus 1,000 pi. But if r is equal to h, then we would have, well, we're going to set that equal to 0 first. Negative pi r squared h plus 1000 pi is 0. And if r is equal to h, that's negative pi r squared times r plus 1000 pi is 0. So it's just negative pi r cubed plus 1000 pi is 0. And if we divide by pi, negative r cubed plus 1000 is 0. And so r cubed would be 1000. And r, the cube root of 1000, is 10. So then r is 10. I guess we'd be in centimeters, right? And h, which is the same as r, would also be 10 centimeters. Okay, so a little bit tricky because of variables and such. But again, this is going to be more straightforward with x's, y's, functions given. Looks like we're going to need part 3 for this lesson. Just one more example. Should take about 10 minutes, but we're already at the 22-minute mark, so I think I'll cut this one short.